In this video, we're going to see another application of derivative of a function. It's called the Newton's approximation method. So with this method, we are trying to find what's called the zero of a function. So given a function f of x, what's the zero of a function? That's when the function value is 0. That's where the function value is 0, so it's the location. From the graph, we can kind of see that at the location A, the function value is 0. Therefore, A is called 0 of f of x. So mathematically, it is the same as basically solution of such equation. So 0 of a function is the same as a solution of an equation in the form of f of x equal to 0. Okay, so in this section there are two types of problems. So sometimes they say, hey, find the zero function, or they say approximate solution of an equation. That's why. So how do we do it? Well, this Newton's method involves basically tangent lines. That's what it means. So how it works is you pick up an initial location called, say, x0. We'll talk about how to pick up the first location. Okay, just say pick up 1, then at the location x0 on the graph, you draw a tangent line. That's why this basically is a tangent line approach. So we can, write an equation of the tangent line, because the derivative at this location is going to be slope of this straight line, and we know the location is x0, f of x0. So we write an equation of tangent line. So we write an equation of tangent line. So that's equation that represents this yellow straight line here. Then we find the intersection of this line x-axis. Call this location as x1. Now, once you find the equation of a line, you can set the function value to 0 to find this location. So pretty simple math. So find x1. And at this new location x1, you do another tangent line. You do second tangent line. Again, find the x-intercept of this line called x2. Okay? Wait, repeat this. At the x2, you do a tangent line. Find the intersection called x3. Now I think it's clear what we're trying to achieve here. So by finding a sequence of tangent like this, we're getting sequence of intersections x1, x2, x3, which are apparently approaching the actual intersection of the graph of f of x with the x-axis A. All right. So mathematically, how do we achieve that? Well, remember the first tangent line we obtained at x0. So like I said, you write down equation of tangent line and set the y equal to 0 to find x1, and turned out you would find this. Okay, so this expression on the right side will give you the x-intercept of the tangent line here. So you find x1. Now similarly, you write an equation of a tangent line to the graph at a location x1 and set the function y to 0, and then solve for x. You find this to be your x2. All right, so this way we kind of see that all these expressions for the new location will take the same exact form of x minus f of x divided by f prime f of x. So this is what we summarized as the generator, the value, the expression that's going to generate new value. I call it as Newton's function. Now with that, you look back and say, hey, how do we get x1, and how do we get x2 from x1? How do we get x3 from x2? So basically, it shows that we just need to plug in, for example, x1 into the function to get x2. Once we find x2, we plug in to x2 for x to get x3. Just keep plugging the new value to get the next one. So this is like the generator, the number generator. As we can see from the illustration here, numbers generated in this order will be approaching the actual zero of function or solution of the equation. So you do this no more than 5 times. The value you obtained will be very close to the actual value. Okay, so pretty simple. And this is considered as some application, one application of derivative, because derivative of a function is involved. Okay, let's see one example. So here, let's find an approximate solution of cosine x equal to x. So this is an equation. We're trying to find the approximate solution of this equation. So first, we need to determine the function involved in our problem, so we can apply this Newton's approximation method. Okay. Well, one thing I want you to know is you need to move all the terms to one side to determine the function. So cosine x is not f of x. Cosine x minus x equal to 0. In the equation here, the left side of the equation is the function. Okay, move everything to one side to determine the f. So f of x is cosine x minus x. Now, remember the formula here, the generator, Newton's function. So for f of x in this problem equal to cosine x minus x, this generator function is x minus a function on the top, f on the top, f prime on the bottom. You see, you just differentiate the f. Make sure the order is correct. F on top, f prime on bottom. In between is subtraction. Okay, so with this, we can start to generate the numbers. Let's pick up location 1. So I was saying, I will talk about how to pick up the first location, right? Generally speaking, if an interval is given, you probably want to pick up the middle point. For example, if you are asked to find approximate solution between 1 and 5, Okay, then you probably want to pick up the middle point, which would be in this case 3, because 1, 5, 3 would be right in the middle. Okay, this would speed up the process a little bit. Also, this way, when everybody picks up, the same starting point, I'll be able to compare results. All right. So anyway, so if there's interval given, pick up a middle point. If not, you just pick up any number to try. All right. But most of the time, there will be an interval given. So in this case here, we're going to just pick up a 1 to try it out. So pick up 1. What do we do? Plug in 1 for x in the Newton's function here. 1 for x. So basically our x2 will be calculated by evaluating basically the Newton function at x equal to 1. So 1 plug-in for x, 1 plug-in for x here. So it's 1 minus cosine 1 minus 1 over negative sine 1 minus 1, and simplify. Now when trig functions are involved, set the mode to reading. So it'll be x1. So x1 will be with the calculator 0.7503. Okay, with x1, then we do x2. How do we do that? We plug in x1 for x in the Newton's function. So it'll be, you write it one more time. So it'll be 0.7503 for x minus cosine 0.7503 minus 0.7503. It's hard to write with the stylus. Over negative sine 0.7503 minus 1. Okay, so let me just kind of show you. So this is basically x1. All right, and then again with a calculator, you can find to be approximately 0.7391. So this is x2, and then the next x3. I'm not going to plug in any gesture, So I would plug in this for x, and simplify the right hand side. I get x3 from x2, right? This is x2. From x2, I'm going to get x3 as a 0.7308. And then plug in x3 value here for x. Now get x4 to be just repeating the same kind of computation. All right. So as you can see, there's no difference between x4 and x3. Then we can stop. If you don't see identical answers, stop at x5. Be good enough. All right. So our conclusion: this is the approximate solution of this equation. This value is accurate to the 4th decimal point. All right, so it's pretty simple. All right. let's stop right here.